Thanks so much, Michael, and thank you all. Today I'm going to talk to you about Raft-Forensics, which is a system for providing crash fault tolerant consensus with accountability for Byzantine faults. This was work with some amazing collaborators, and in particular I want to highlight Wei Zhao Tang, who is a PhD student here and is going to be graduating in the next year, and he was the lead on this project. So today when we talk about fault tolerance in distributed systems, there's two main types of fault tolerance that we typically focus on. One is crash fault tolerance, which is robust to nodes that crash. And the other is Byzantine fault tolerance, which is robust to nodes that misbehave in arbitrary ways. Now, even though we focus on Byzantine fault tolerant or BFT protocols pretty widely in the blockchain community, in the broader world, CFT protocols are much more widely adopted in enterprise settings. And in fact, recently CFT protocols have been gaining adoption in critical infrastructure. So one example of this is central bank digital currencies, or CBDCs. So a lot of the designs for emerging CBDCs are using some form of crash fault tolerant protocols. So why is this? Well, even though CFT protocols have weaker security guarantees, they win in terms of performance typically. They have higher throughput and lower transaction confirmation times. Whereas BFT protocols are able to tolerate a stronger form of faults, whereas they have worse performance. So in this work, we asked, can we get the best of both worlds by providing accountability? That is, what if we didn't need to tolerate Byzantine faults, but could instead point to the culprit if a Byzantine fault occurs? So in this work, we modified Raft, a widely used CFT protocol, to try to provide such accountability guarantees, hopefully taking only a small hit in terms of performance. So the model here is roughly that we have a client that's submitting transactions to a set of nodes who are in charge of maintaining a ledger. We assume that some fraction of those nodes can crash. This is the crash fault tolerant model. Now, vanilla Raft, the protocol that's widely adopted today in industry, satisfies state machine safety, meaning that no two of these server nodes, the green nodes, will ever have conflicting entries at any index of their logs. Now, what we did in this work was to extend this model just a little bit. So we allowed one of these nodes to be malicious. And we only allow one node to be malicious because that's all that's needed to break consensus in both Raft and other CFT protocols. In addition, we allow the presence of an auditor who's allowed to query our server nodes, the green nodes, for their logs. Now, the property that we want to satisfy is that if a state machine safety violation exists, meaning if two nodes disagree at a particular index, this auditor should be able to point to at least one Byzantine node, a node that did not follow protocol. Okay. Now, satisfying this problem isn't too difficult in general. You can come up with a number of protocols that satisfy this property. What's delicate is finding the minimal set of changes that we need to add to Raft or any CFT protocol in order to provide this accountability property. So we did this exercise. We derived Raft-Forensics, which is a modification of Raft that provides accountability, provably, and implemented it over new Raft, which is a C++ implementation of Raft that's used in a lot of big systems, including Kubernetes. And we implemented it with the performance shown here. So here on the horizontal axis, we have throughput. And on the vertical axis, we have confirmation latency. So we want to be really in the bottom right-hand corner of this plot. And you can see that Raft, is the blue curve, has the best performance of all of the protocols we compared against, whereas these two protocols are BFT protocols, and so they have worse trade-offs between throughput and latency. And the orange curve, which is Raft-Forensics, this is the one that we developed, takes a small hit in terms of performance while being able to provide this accountability property. So the takeaway here is that accountability can be an inexpensive alternative to Byzantine fault tolerance. We're currently integrating and evaluating Raft-Forensics with OpenCBDC, which is an open source implementation of a CBDC that's developed by the MIT Digital Currency Initiative, as well as the Boston Federal Reserve. So if you're interested, you can check it out on GitHub, and we have a paper coming out soon. Thank you.